All right, so for today, we're going to talk about distributed loads. So every force we've seen so far acted at one single point. Distributed loads are things that are much bigger, things like a big piece of furniture maybe, or snow on your roof, something that extends over a very large area, and therefore the force is not just at one single point, it's spread out over some big distance. So how do we deal with those? So other examples, fluid pressure on a dam or retaining wall. We'll see some of that in a few weeks later in class. The weight of a beam itself. So if you have a really large beam that's very heavy, the beam has to support not only what's above it, but itself as well. And so that may have to be part of the calculation. And so if you have a homogeneous beam, the weight distributed along it will have to be in the calculation as well. So these large forces essentially cause pressure. So the weight of the snow causes pressure on your roof. And so that's called the intensity of the loading, usually in units of pressure, which are pascals in metric units or pounds per square foot in the US units. Now, we don't necessarily want to look at the entire two-dimensional pressure being created. We're going to assume that everything's uniform in one of those two directions. So we're basically taking that area down to a one-dimensional length and just looking at the weight distribution along that length, which may be constant or it may vary as well. So in and out of the page, we're assuming everything is the same, but along the length of this beam, I could have a different loading function based on whatever's happening, the weights of the object above it. So I basically turned that pressure, P, as a function of x, multiply that by the width of the beam in and out of the page called B, and that brings me to this one-dimensional loading called W. So W of x is basically how much force I have at each location x along my beam from 0 to L. And that's going to be in newtons per meter or pounds per foot because it's has an extra feet or meters in it when I multiplied it. So that's going to be the units for W of x. Anytime I have an intensity of loading is going to be in either pounds per foot or newtons per meter. So what we want to do with this is similar to what we did in the previous lectures, is to take this distributed load and turn it into one single point load. So one single concentrated load at some specific location x bar that does the exact same thing in terms of translational and rotational properties. So I want this total force Fr to equal the total net force downwards from my distributed loading and also produce the same moment that this distributed loading does as well. So two questions to ask now is how do we find the magnitude, Fr, and how do we find this location, x bar? So kind of extending what we did in the previous classes. Previous classes, I just took a whole bunch of forces and added them together to get the net force. I took those forces times distances, added those together to help me find where to locate this one single force. So same thing here, except now I'm not dealing with a lot of point forces. I'm dealing with one big long distributed force, which I can kind of pretend is an infinite amount of point forces essentially. And if I'm adding up an infinite amount of point forces, that summation turns into an integration. So basically all I need to do is integrate that loading function W of x over the entire length of the beam from 0 to L, and that gives me the total net force pushing down from the distributed loading. And so that should be the magnitude of the point load that I replace it with. So that's how I'm going to find the magnitude of that single point load that's equivalent to the distributed load. Now, if you remember calculus class, if you take the integral, that's the same as the area under the curve, and the function that I'm integrating is this curve W of x. So really what I'm doing is I'm finding the area under the curve. So another way to find what the magnitude of this point load should be is to find the area under the curve, and that's going to be helpful when we run into some simple distributions. So not this kind of weird curve one I have here, but there'll be a couple simple ones that we run into a lot, where it might just be easier just to calculate the area as opposed to doing these integrals. Now, in terms of the moment, the way we found the moment is basically by balancing the moments on either side. In other words, this FR times this distance x causes a moment, and that has to equal the total moment that was produced by all the other forces acting. And so I took a whole bunch of these forces times their distances, added them all up, and had that on one side, had FR times X bar on the other side, and then divided by X bar to find, divided by FR to find X bar. Again, here, instead of adding up all my forces times distances, I'm going to have to integrate. So a force pushing down, in this case, is W as a function of X, and then it's located at some location X. So X times W of X gives me the individual moment from kind of one individual little infinitesimal force, and then integrate that from 0 to L gives me the grand total of the entire moment produced by this distributed loading W of X. So this is the moment produced by the distributed load. That's why I call it MD, D for the distributed loading. And then, as I mentioned, that has to equal the moment produced by my single equivalent point load, which is FR times his distance, X bar. So X bar times FR has to equal MD, which is this integral. And so simply divide by FR, and that gives me this equation for X bar. So integrate X times my loading function from 0 to L, divide that by the FR that we just found using the other integral, and then that gives me X bar. FR obviously was found from this integral on the bottom here without the X. Now, some of you who may love math may realize that this equation is actually a very special equation. And what this actually gives me mathematically is the centroid of the area. So just like for the magnitude of the force, it's the area under the curve. For the location of the point load, I should be looking at the centroid of the distributed loading. So whatever that curve does, whatever that area that's produced by it, the centroid of that area is actually where to put this equivalent point load FR. So that's, again, another way that I can determine where to put this instead of using the integral for some simple shapes that we'll see later. So kind of summary, centroid right in the middle, X bar, that's where F bar should be located, and F bar is the total area under the curve. Now, as I mentioned, there's a couple special cases that we see a lot. The first of which is to have a constant or uniform loading. So my weighting function W of X is just some constant C. And this happens a lot for things like, again, snow load on a roof. If you have the same depth of snow everywhere on your roof, it's producing a constant loading everywhere. Same thing for the weight of the beam. So if I'm looking at this beam and it has a fairly large weight to it, I want to take that into account. And assuming it's homogeneous, then the weight's going to be distributed evenly along the entire beam. So again, this would be a uniform or constant loading. And so for this constant loading, I want to now find the equivalent point load, so a magnitude and a location of where that belongs to cause the same rotational and translational tendencies, same overall net force, same overall net moment. And so again, I kind of do this the long way using the integrals. So W of X in this case is just some constant C. I want to integrate that from 0 to L. So integral of a constant is just C times X. X from 0 to L gives me just C times L. So that's the magnitude of this load, FR. If you think about this loading, so this curve, W of X equals C, C is essentially the height of where this line is. And so C is the height of this rectangle, L is the length of this rectangle, and so area of this rectangle is just C times L. So like we said, a shorter way to do this is to find the area under the loading. In this case, the loading is a rectangle, so just base times height, L times C. Similarly for location, I integrate x times the loading function, so x times c. Integral of that is 1/2 x squared times c. And then I also want to divide by the FR I just found above, the magnitude CL. So cx squared over 2 from 0 to L gives me CL squared over 2. But then I want to divide by C and L. So that gives me a grand total of L over 2. And L over 2, halfway through my beam, right down the middle, that is the centroid of a rectangle. Obviously, rectangles nice and symmetric, so centroid's right in the middle. And so that's where my loading belongs. So kind of shortcut for uniform loading is to just do base times height as your magnitude and put it right in the middle. The other special case that happens a lot is a linear distribution. So it looks like a triangle in terms of my weighting function W, officially given by C times X. So again, C is the constant here. It kind of represents the slope of the line. And again, X is my value from 0 to L. So I kind of let you check out the math, do it on your own. Make sure that these integrals work out to what I tell you they work out to. But in terms of the magnitude of my equivalent point load, it's 1/2 CL squared. And again, that's the same as the area under this triangle, 1/2 base times height. Base in this case is L, just like it was before. The height of this, so basically what I want to know is what is this height, which would be represented by W of X when X is equal to L over here. So when X is equal to L, this has a weighting function of C times L. So the height of this triangle is C times L. So 1/2 L times C times L is 1/2 CL squared. So that's the magnitude of this equivalent point load, FR. And in terms of where to put it, I put it at the centroid. You can either look up the centroid of a triangle or again, do the integrals that we saw for the previous case, do those in this case, and you'll find that X bar is 2L over 3. Centroid of a triangle is 1/3 from the big side. So big side in this case is the right-hand side. So you go 1/3 in from the big side, L over 3 is where I put that point load FR. So 2/3 from the small side, 1/3 from the big side. So again, instead of having to do those integrals again, anytime you see a triangle, you can just put it 1/3 from the big side, magnitude of 1/2 base times height squared. Sorry, 1/2 base times height. Or 1/2 CL squared if you're given the slope. So that is how to deal with distributed loads. So be sure to come to class today, or again, whenever class is for you after watching this video. And we'll do some examples of that. And then after that, we'll actually, next video will involve rigid body equilibrium, which is really the biggest part of this class, kind of the most important topic of this class. So actually the next 2 videos are going to be covering topics from that because it is so important. So be sure to come back for those.